Let's take a look at 3.8, continuing in 3.8 on related rates and examples. So the next thing I want to do is give you some basic outline of guidelines to solving related rate problems. And this is just a general guideline, kind of remind you of how to do word problems and a few particulars of related rates. So one, and there's an outline in the book. I always go through it myself and kind of do my own version of this. So look at that as well. This one's kind of more a sketch and an outline of what to do and kind of my own input on it. So first, read the problem more than once, and I'll write it all out for you. So read more than once. So read it a couple times before you start doing that. And as you're reading it, basically, I want you to determine unknowns. You're making a mental note right now. Okay, what are the unknowns? What are we looking for? So determine the unknowns. Later, you'll write them down and define a variable, but okay, 2, you've read the problem. They talk about stuff. Now I want you to sketch a diagram or a picture. Always really important. So sketch a picture or diagram. And start labeling it. So you're going to label lengths, widths, heights, that kind of stuff. 3, write down all known and unknown variables. Known and unknown variables. So if it says, the height of the cone is this, you write down h equals and label all of it. So the next part's usually the most difficult, and that's basically set up an equation. So write down, the way I put it here basically is write down, oh, sorry, I was going to do that. Write down all known and unknown variables. Okay. Next, 4, set up an equation. So this is where back in algebra, often you could just figure it out by plugging in numbers. And your teacher would be, no, if they're good anyway. They'd say, no, don't write down the numbers. I know you could figure it out. I want you to set up an equation to solve it. And you're like, oh, I can't, I can just figure it out. Well, now you can't just figure it out. Now you have to set up an equation. Hopefully back then they made you. I would have. So set up an equation or use a formula. Like Pythagorean theorem, volume formulas, that kind of stuff. So use a known, I'll just say known this time, known formula. Or variation thereof, something that you have to do. This is one of the most critical steps here, is setting up that equation. Now you have to differentiate. So you differentiate implicitly with respect to time, because it's a rate. Differentiate explicitly with respect to time. T. Okay, then 6, now you substitute and solve. One of the most common mistakes is to substitute back here or here before you differentiate. So you got to differentiate first and then substitute and solve. Otherwise, you'll get stuff just annihilating and simplifying out. Very general guidelines, because a lot of this is getting used to how to do it. But that should help us a little bit. Okay, let's look at this first example. Okay, it's example 1. And hopefully we'll use the guideline to go through it. Okay, so air, I think this is similar to what the book might have, but that's okay. Whatever's there is fine. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. So we know the units are appropriate. Find the rate of change of the radius when r is equal to 2. And I copy this. That's when, not with. So when r is 2 feet. So rate of change, you got to figure out, well, what's rate of change? Oh, this is when, not with. When r is equal to 2 feet. All right, so read it again yourself. I read it plenty of times, so I'm not going to read it again. But read it again. What is it saying? Well, when you go through, you want to start sketching a diagram or a picture and start labeling. And you can do things together. I mean, you don't have to do this in order. I mean, you want to write down unknowns and that. So I think I don't know if the book actually had r equals 2, but now I'm saying it is. I'm saying when the radius is 2 feet. So I'm looking, what I see here, I see spherical, balloon, and volume. So what I would do right away actually is go to number 3 and just write down volume equation. The volume of a sphere is 4/3 pi r cubed. And I just know that because of the formula. I know I'm going to need that. And then I would start sketching a sphere. So I would sketch my sphere like that. And just has to be, I'm going to do it dotted just because I can. In the background here. And then the back of this will be dotted as well. And the front will be solid. There, that looks pretty good. Okay, so I have a sphere, radius r. So I like to do my graph like that. This is one of those cases you probably don't need a diagram because it's really just you're not going to do any work with it. But I still recommend always thinking in terms of drawing a diagram. You want to visualize this stuff. So, so what are we looking for then? So we're actually looking for, so find the rate of change of the radius when r is equal to 2. So we're actually looking to find what? So you want to find dr dt. That's rate of change of the radius. What else are we given? So we're given this. We're given 4.5 cubic feet per minute. So what is that? That's dv dt. So we're given dv dt is equal to 4.5 cubic feet per minute. Oh, okay. So now we want to, we have our formula kind of already done for us. This is somewhat easier of a case. We're looking for dr dt. We're given dv dt. So what's next? So we've written down all unknowns. We've labeled. We have our equation. We used a known formula. Well, next is 5. We want to differentiate implicitly now. So derivative of v is just 1. So you get dv dt equal to, that'll be 4 pi r squared. And then times what? Times dr dt because of chain rule. So we're solving for dr dt. So this is what we want to find, right? So that's your find piece. Am I playing too much? I don't know. Okay, so find that. And you're given those other values. So now basically substitute in and solve. And again, that's the easy part. Okay, so let's substitute and solve. We get 4.5 equal to 4 pi r squared. I'll just write it as 4 times, and then dr dt. So dr dt, you just divide both by that, is equal to 4.5 over 16 pi. And of course you get an approximation of that because it's a decimal. But that'd be, as close to exact as you would need. So it's 0.089. And then what are your units? It's your this tells you your units. It's your radius is length, which is in feet, and then your time is, of course, just, minutes. So this is feet per minute. So this is feet per minute. Okay. Let's see what else we got. Let's do another one. So this one is the right cone one. Okay, so I'll just write it all out for you. A water tank has the shape of a right, meaning it's not skewed in any way, cone, circular cone, of altitude 12 feet. So the height, right? The height of it. And base radius, so the radius where it stops, 6 feet. So if it's a water tank, is it go like small at the bottom and go up like an ice cream cone, or is it reversed? So does it look like this, or does it look like this? So yeah, it has to look like that because it's holding water. Okay, so it really wouldn't matter technically, but you gotta visualize this right. So I'm gonna get rid of that. I don't want that stuff in there. We'll draw a better picture. All right, so the question is, if water is being pumped in, okay, so if water is being pumped in at 10 gallons per minute, approximate the rate at which the water level is rising when the water is 3 feet deep. A little note, 1 gallon of water is approximately 0.1337 cubic feet. Seems small, but whatever. Okay. So let's start writing our stuff down. So this time I'm going to draw a picture first. So I'm going to draw in my right cone. Oh, that didn't work out too well. Let's try that again. There, that looks pretty good. And then it's I'm going to center that so we can get it to look pretty good. So here's our cone. That missed completely. If it looks like I'm being really, really careful, it's because I am. It's just occupational hazard. It's just what we have to do. So I kind of get good at doing this sort of stuff. All right, so you have an altitude up to here. You have a radius, right, the fixed one, and then water is going to be filling up. So the fixed values I'd like to write down next. So let's write down some fixed values. Let's change the colors so we can make it look nice. We'll do it over here, get it out of the way. Oops, let me get that back. Okay, so whoa, come back here. Okay, so here's the fixed value. So the fixed height is 12 feet. And then you get this. And what's the fixed base radius? It's up there. Yeah, the base radius is 6 feet. So that right there is 6 feet. Okay. Now, we're going to be pumping water into this thing. So let's get some water in here. 3 feet high. So 3 feet is basically right in here somewhere. Okay, so we got water in it. We want to know what it is at 3 feet. What's happening at 3 feet, basically. So right about here. But you don't want to put in the 3 feet yet. That's the mistake that can happen. So we're going to have a radius somewhere, and we're going to have the relative height of that. So we're going to have h. So we're going to look at basically this triangle and then this triangle. And we're going to end up using similar triangles. All right, so let's write down some more information that's given. What else did it tell us? If water is being pumped in at 10 gallons per minute, so your dV, let's leave that color, it's fine. dV dt is 10 gallons per minute. All right, so I'm going to give you this straight up. This is basically one, without messing this up. So it's 1.337 cubic feet per minute. Using that conversion. So what are we trying to find then? All right, yeah, so find the at what rate is the water level rising? So we're looking for a rate again. Doesn't all have to be rate. It could be finding R or H. So it could have given you rate, but it actually wants you to find rate. So water level rise, was it dRdt or dHdt? It's dHdt. So find dHdt because that's height. Find the rate, the water level is rising. Find dHdt when H is 3 feet high. So we want that to be 3 feet. So the problem we have here is we have too many variables. So what we need to do is use similar triangles. So you need to use similar triangles to find R in terms of H. So I'm going to copy this and blow it up and do my similar triangles. Okay, so we're going to put this down here, and I'll just use a whole page for this example. Okay, so there's my triangle, and then somewhere in here is your R. Okay, so there's your similar triangles. So this is 12, 6, R, and then here's your H. So you can write R is to H as 6 is to 12. All right, you know how to do all that. So R is equal to H over 12. So now look up volume of a, so we could have done that back here. What is volume of a cone? So volume of a cone is 1/3 pi r squared, or h squared, I'm sorry, 1/3 pi r squared h. So it's the radius and then times the height. So it's basically 1/3 pi r squared and then times the height. So that's the formula we're going to be differentiating. But we got to substitute for a variable. So now substitute, and we get volume is equal to 1/3 pi h over 2 squared times h. Simplify that and you get 1/12 pi h cubed. Okay, now differentiate that. So now differentiate. And we get dv dt, so derivative of v is just 1, equal to, now you just have one variable. So that's pi fourths, bring down the 3 and reduce, right? Pi fourths h squared times dh dt. And aren't we looking for dh dt? Yeah, we're looking for dh dt. So now we can substitute, and this would have been a critical step here, sometimes easily missed. So we get 1.337 is equal to pi fourths times 3, because that's, it said when it's 3, so that's, I'll just say 3 squared, so you can hopefully see that, times dh dt. Okay, and then you solve, and I'll spare you the little details there. You get dh dt is approximately 0.189 feet per minute. So, what, almost 0.2 feet per minute when, as the water is being pumped in. So it'll slow down, right? At first it's going to go fast. Then as it continues up, let me do this so you can see everything. So it's going to be rising kind of fast, and then it'll slow down because it's the same rate, but you have more volume up here. So the rate's continually changing. And that's what we mean by a rate that's related. It's related to the dimension of the whatever we're using. Okay, let's see. I have a couple more. Well, I have one I'll just show you since we're here, and then we'll probably just practice more altogether. So I'll just copy this one over. This is what I have. There's another typical one. I wasn't able to copy this the other day. I'm not sure why it's doing that. Okay, let me just see if I can bring it over. Well, that's it, but I want it in the other deal over there. So let's copy that and paste it here. Okay, and that didn't work. Let's try that again. Oh, you know what? I need to paste picture, paste image. Okay. So you can try this one. Let me erase some of this stuff here. Oh, it pasted the whole image. Oh well. So, ignore this for a second, and you can try this one. It's a pretty straightforward one. And this says form concentric, that says concentric circles is increasing at a constant rate of 1 foot per minute. And then rate is the total. So that's really, I'll write that in. So that's just concentric That's just at a constant rate. And this is, at what rate is the, I think, total. Is that right? It doesn't really matter. At what rate is area A of the disturbed water changing? I think that, yeah, that's total. Okay, so you can try that one, and then we'll probably just do more in the problem sessions as well.